Newton's grasp of gravity was sufficient to make it possible for humans to leave Earth to the moon. Have you ever found yourself immersed in the ticking passage of time, assessing whether our comprehension of it only scratches the surface of teen, as if a vastly greater, unobservable reality? Is his insight a key, rather than just a hypothesis? That could provide access to the universe, revealing a much larger cosmos, more complex and inspiring than we ever imagined. How does Brian Cox's latest theory alter our conventional understanding of time? And what might it mean for our way of life and how we perceive reality? Come along with us on a fascinating journey through the fabric of time itself in our investigation of Brian Cox's groundbreaking ways. And it's groundbreaking. New hypothesis regarding the way time works and the vastness of the universe surrounding us. Unsolved enigmas await. Discovery. Some puzzling aspects of time and gravity-critical elements of the universe. Imagine a world in which time behaves in unusual ways. They're slowing down or accelerating. The force that holds us in place may not be what it seems. This is the domain of Albert Einstein's theories of relativity, in which our comprehension of both gravity and time takes an unexpected turn. Einstein's family name changed the way we understood the universe. The theories he developed laid the basis for describing how time functions under different circumstances, especially when traveling at high speeds. It all started at the beginning of the 1900s, when Einstein introduced two groundbreaking concepts, special and general relativity. The special theory of relativity, published in 1905, fundamentally altered how we view time and space. Simply put, it asserts that the laws of physics are identical for all observers who aren't accelerating despite their movement. This theory introduced the notion of relativistic effects, including the now well-known idea that time can either slow down or speed up under certain circumstances. An intriguing thought experiment used to illustrate time. Dilation involves a light clock. Picture yourself inside a spacecraft traveling almost at the speed of light. Inside the ship, there's a beam of light bouncing between two mirrors oriented in the direction opposite to travel, according to the laws of physics. The speed of light is constant for all observers. So, to someone observing from outside the ship, the light would appear to take a diagonal path. The amount of time it takes for the light beam to travel its path should be identical for both the observer inside the ship and the one outside. However, because the route appears longer to the outside observer, it seems to take more time for the light to complete its journey. This apparent disparity in distance between the two observers is what Einstein described as time dilation. For the observer in motion, time slows down relative to the stationary observer. Thus, time behaves differently depending on the observer. The effects of special relativity, how things behave when moving rapidly, are more than just theoretical. Scientists make use of massive machines like particle accelerators to speed up particles to nearly light speed. At these speeds, time behaves in ways that demand special consideration for accurate predictions and measurements. Einstein's special theory of relativity, published in 1905, transformed our understanding of the universe, particularly regarding time and motion. It tells us that the laws of physics are the same for everyone, regardless of how they move. This runs counter to our everyday intuition, where we assume that adding more speed simply makes something move faster. But according to Einstein, there is a cosmic speed limit, the speed of light. Events that occur simultaneously to one observer may not appear simultaneous to another, moving near the speed of light. Special relativity also introduces the concept of length contraction. An object moving at high speed appears shorter when viewed from the perspective of a stationary observer. One of the most famous outcomes of this theory is the equation E equals mc. This equation reveals that energy and mass are interchangeable. It is essential for understanding how particles behave at high speeds and underpins nuclear reactions when atoms split. Special relativity isn't just an abstract idea, it's crucial for modern technology. For example, GPS satellites orbiting Earth move quickly and experience time differently than people on the ground. If we didn't account for this time distortion, navigational systems would be far less accurate. Therefore, special relativity teaches us that time is relative, depends on how things are moving, which challenges our common sense understanding of time and space. But the story doesn't end there. Enter Einstein's general theory of relativity, published in 1915. This theory delves deeper into the relationship between gravity and the structure of the universe. It challenges the conventional notion that gravity is merely a force pulling things together. Instead, it posits that gravity arises from the curvature of space and time. In other words, gravity isn't some mysterious force, it's the natural result of how mass warps space-time. To understand general relativity, imagine the universe as a four-dimensional fabric, 3 dimensions of space and 1 of time. Massive objects like stars, planets, and even humans warp the space-time around them. This warping is what we perceive as gravity. Think of space-time as a large elastic sheet. When a heavy object like Earth rests on it, it creates a depression. Place a smaller object nearby and it will roll toward the dip. This is analogous to how gravity works not as an invisible force, but as the result of curved spacetime. Earth's mass creates a dent in the spacetime fabric, and other objects move accordingly. General relativity provides a comprehensive explanation for our planet's motion. It accurately predicts the elliptical orbits of planets around the Sun. This approach differs from the old idea of gravity as a force simply attracting objects. The modern view that space and time are curved more accurately describes observed planetary behavior. A significant confirmation of general relativity came in 1919. During a solar eclipse, Sir Arthur Eddington led a team to observe how the light from distant stars bent as it passed near the Sun. The observed bending precisely matched Einstein's predictions, providing strong evidence for the theory. Just as motion alters the passage of time in special relativity, gravity also affects time. In regions of strong gravity, time moves more slowly compared to areas with weaker gravitational fields. If you stood close to a massive object like a black hole, your clock would tick more slowly compared to someone far away. This concept, first introduced in general relativity, revolutionized our understanding of the universe. The concept of black holes as regions in space where gravity is so intense that nothing, not even light, can escape, is central to modern astrophysics. The boundary of a black hole is referred to as the horizon, which denotes the point of no return. Once something crosses this boundary, it is permanently drawn in. Einstein's general theory of relativity has far-reaching implications for our comprehension of the universe. Initially, Einstein included a cosmological constant in his equations because he believed the universe was static. However, when it was discovered that the universe is expanding, he acknowledged that the constant was incorrect. This expanding universe, as described by the Big Bang theory, is centered on general relativity, which explains the origins of the cosmos. Another crucial concept from general relativity is gravitational waves ripples in the fabric of spacetime, caused by extremely massive objects like neutron stars or black holes colliding. In 2015, scientists at LIGO detected gravitational waves for the first time, providing further validation of Einstein's predictions. Over the years, numerous experiments and observations have consistently affirmed general relativity's accuracy, whether through observing planetary orbits, light bending, or detecting gravitational waves. While the notion that gravity is a lie might seem shocking, especially considering our daily experiences with it, is not uncommon in science to question established theories. Some scientists, including Brian Cox, challenge conventional theories of gravity and explore alternative explanations. One such idea is modified Newtonian dynamics, MOND, which suggests that gravity acts differently at low accelerations, especially in galaxies and may eliminate the need for dark matter, instead of invoking invisible matter. Proposes that gravity becomes stronger at lower velocities. The debate surrounding gravity also intersects with mysterious phenomena like dark matter and dark energy, which were introduced to explain certain cosmic observations. Critics argue that these concepts may not be necessary and that alternative theories could explain these phenomena. Some scientists who dispute Einstein's theory of gravity explore new possibilities such as unknown particles or forces that could revise our understanding of gravity. In science, new ideas are rigorously tested to determine their validity. Einstein's concept of time, viewed as a dimension within four-dimensional space-time, led to speculation about phenomena like wormholes and shortcuts through the universe. Stephen Hawking's chronology protection conjecture suggests that time travel into the past is likely impossible from a physical standpoint. Ongoing experiments and observations test whether these new hypotheses can describe gravity in ways comparable to our current understanding. Despite differences and proposed alternatives, none have convincingly replaced the established laws of gravity. Challenging and questioning established ideas is a critical aspect of scientific progress, leading to deeper exploration and more refined theories. In the realm of gravity, general relativity remains the most successful and widely accepted theory. It continues to perform well in tests and explains a wide range of phenomena, such as planetary motion and the bending of light around massive objects. Its simplicity and universal applicability help ensure that general relativity remains the dominant theory. We can only continue to push the boundaries of our comprehension, fueled by the extraordinary work of scientists like Brian Cox, who invite us to explore new ways of thinking about gravity. As we continue our exploration of gravity and time, it becomes clear that scientific advancement depends on our willingness to test and refine existing theories. With the development of technologies like gravitational wave detectors and space telescopes, our capacity to test the boundaries of general relativity and develop new hypotheses is more effective than ever. Whether it's exploring the nature of black holes, dark matter, or speculating on the actual structure of the universe, scientists are expanding our understanding in a fascinating quest to reconcile general relativity with quantum mechanics. While general relativity excels at explaining the behavior of large-scale objects like planets and galaxies, quantum mechanics governs the interactions of very small particles like those at the subatomic level. These two frameworks, despite their incredible success in their respective realms, are fundamentally incompatible in certain areas. The search for a theory of everything, a unified theory that explains both the quantum world and the large-scale universe, has become one of the most difficult problems in modern physics. Concepts like string theory, loop quantum gravity, quantum field theory are among the leading candidates for bridging this gap. Yet at the moment, the mystery of how to merge the very large with the very small remains unsolved in this rapidly evolving landscape. Brian Cox and other scientists continue to investigate novel concepts and offer new perspectives on well-known ideas. Cox's work, which combines theoretical physics with public outreach, helps make complex topics like gravity, time, and the nature of the universe more accessible and engaging. His insights challenge us to rethink not only the nature of gravity, but also the way we perceive reality itself. What does it all mean for the future of science and humanity's understanding of the universe? As we step into the unknown, one thing is certain: our journey has only just begun. Each discovery, each breakthrough opens up new questions and additional mysteries waiting to be unraveled. With curiosity as our guide and science as our tool, there is no limit to what we can accomplish in our efforts to understand the connectors. I've started the fundamental forces that govern the cosmos, whether it's reimagining the nature of time or unlocking the elusive secrets of gravity. The road ahead promises boundless wonder and exploration. And with researchers such as Brian Cox leading the charge, the mysteries of the universe seem closer than ever to our grasp.